Thank you to the organizers for putting together a very nice meeting. So today I'm going to talk about singularity formation in the Euler equation. So this is going to be the topic for all three of the lectures. So today I'm going to talk about sort of some basic things about transport equations. And at the end, I'll talk about applications to Euler. And yeah, so the 2D Euler equation is, we all learned last week, I hope, is a nonlinear transport equation. So vorticity and U is determined by the Biot-Savart law. In domains with a boundary, this inverse Laplacian means the Dirichlet inverse Laplacian. When you have multiply connected, okay, maybe you need like a domain with holes. You need some more information to recover the velocity from the vorticity, but okay, we don't think about that. We just think of the basic. So we should really view the Euler equation as having two pieces. So this is the transport part. And this you could say is like an elliptic part. Okay, so the transport equation, as we all know, so the transport equation, you solve it by the method of characteristics. So you introduce the flow map. So phi, which it's a function from the domain to itself and depends on time. And it satisfies the ODE. And okay, it tracks the motion of a point. So phi of xt is the position of the point of the particle that started at time 0 at point x, right? Say that again?
What is the spatial domain?
Okay, so we don't, so x could be, so the spatial domain for us could be R2, it could be the 2 torus, or it could be a channel. Okay, or it could be anything that's similar to this. Okay, is that enough? Okay. The key fact about, so of course, right, and okay, so this. So key fact is omega 0. So omega can then be recovered as just omega 0 composed with the flow map. Okay? Is that okay? Okay, so in principle, by the way, that you can use this to write a closed equation. So you can write a closed integral equation on phi using the kernel of this operator. Okay? That's just, we won't need it, but just a remark. That's just a remark. Okay, so key property, so that was the method, that's the transport part. So the elliptic part, you recover the velocity field again like this. If you're on T2, you should assume that the vorticity is average 0, so that this makes sense. Okay, but the key, so the key fact about this relationship is that if omega has regularity of degree s, so differential regularity, then normally you will have regularity of degree s plus 1, maybe a little bit less than that depending on what space you're working in. Okay, so omega is in H2, then you can bound it in H3, etc. Okay, which is very nice because you're transporting omega by something that's more regular than omega itself. Okay? So that will be useful in what we are going to do. Okay, so I'll assume that you've sort of done the Udovich theory and all that stuff, so that's just a small review. Okay. So now let's talk more about the transport. So this was introduction. So now we talk about transport equation with autonomous divergence-free velocity field. Okay, so as we said over here, the transport equation is, studying the transport equation is equivalent to studying the E. So in the autonomous case, we know that the velocity is Hamiltonian. So you can write it as a perpendicular gradient of something. And there are two, very important facts. So two important facts. The first fact is that phi is measure preserving. So I don't think we're actually going to use this fact today. Well, I should say phi t. So for every t, phi t is measure preserving, mapping of the domain to itself, the spatial domain to itself. And the second fact, and this doesn't use the fact that U is autonomous. So this works in general. But in the autonomous case, we have a more powerful fact, which is that the stream function is preserved. Okay, so a particle has to travel on the streamlines. Okay, so I don't want to move at the wrong rate, so sorry. Okay, so does everybody see why this fact is true? Does anybody want to tell me why this fact is true?
Because you got the gradient of C against the gradient of C.
Exactly, because this thing is just equal to the ddt of phi dot the gradient C at phi, right? But ddt of phi is the perpendicular gradient of C at phi, right? So that's 0. Okay. So now I want to tell you about that most points lie on most solutions of this equation are going to be time periodic. Okay, so for that I need to give a definition. So it's always cumbersome to give the definition. So critical point I is a point where point x, the domain where the gradient of psi is 0. So for the ODE, this is just a stationary point. So it's a point that doesn't move, right? C is a critical value of psi if C is psi of x for some critical point x. And C is a regular value of psi if C is in the range of psi and it's not a critical point, not a critical value. Okay? That's fine. Forgot one thing. So x is a regular point of psi if psi of x is a regular value. Okay, so this is kind of a very annoying choice of definition because regular point is not critical point, right? Because that would be better, but that's not the right definition, I think. Say again?
You can raise the board and use the one that is...
Oh, sorry. Yeah, sorry. Thank you. Okay, so now we have a very important lemma. It said if x, maybe I should give an example. Sorry, let me. Hang on. So let me give an example. So on T2, and take psi to be sine of x, sine of y. So the very famous cellular flow, right? So the critical points of this, so the critical points are, let's just draw a picture. So critical points are all of these circles, all these, sorry, dots. Okay, and this for me is minus pi to pi. Okay? So all of these points are the critical points. All the other points are so these are the critical points. And the regular points are everything in the interior of these squares, not including the boundary. So the boundary are not regular points, except for these dots are also not regular points. Okay? Does that make sense? I should say, in fact, these are kind of regular points, by the way. So these are limiting regular points. So maybe if we have time, we'll talk about that. The only real not regular points are the ones on the really on the separatrices. Okay, and if you have looked at this before, you know that the level sets, so because of this fact 2, the transport is moving along the level sets of psi, so you should draw the level sets. So the level sets of psi are circles like that. Okay, so from this example, it's easy to conjecture, well, that at least the motion of a particle should be, well, it has to be restricted to these level sets. And the lemma we're going to say is that for any Hamiltonian motion, the trajectory starting from a regular point is time periodic. Okay, so this has to just go around. Okay, so lemma. If x is a regular point, psi, then phi of xt is time periodic. With period, we just call it t of x. Okay, this is second statement doesn't have any value right now. Say that again. Okay, good point. So this here we should require that we're on a bounded domain. So torus is fine also, but let's just require. So R2 would not be fine. So let's just say on a confined domain. Okay, whatever that means. So you'll see from the proof why we use that. Okay. Okay, confined is a bad name. So compact domain. Sorry. Okay, so the proof. So probably. So I want to keep it completely self-contained. So I just tell you everything. So you start with the x. So x is a regular point. And we consider phi xn sequence of points. They all satisfy, these are all regular points. So these are all constants. So psi of phi of xn is psi of x is some fixed value c, is a regular value. Okay, and you have a sequence in bounded domain, compact domain. So it has a convergent subsequence. So can everybody see here? It's okay. Yeah. Okay, so you have a sequence of points. They converge to some limiting point y by continuity. So we're assuming psi is C1 everywhere. By continuity, you must have that psi of y is C. And so y is a regular point. And now regular point means, in particular, that gradient psi of y is not 0. Right? This is the key thing. Right? And what does that imply about the level set? So it implies that the set psi equals c intersected with a small ball around y is just what? It's just a C1 curve passing through y, right? It's just a C1 curve passing through y. Okay, so you have y here, and the level set psi equals c is just exactly some small C1 curve. Now, if you keep going, it's can be really crazy. Right? That can't be that crazy, but in theory, it could be really crazy. But locally around y, it's just a C1 curve. And how do you parameterize that curve? By the ODE. Okay, so it's parametrized by the ODE. Okay, so in a small segment here, all of these points, right? So if you have, so all of these points are just phi s of y, right? For s in some interval, say minus epsilon to epsilon, right? The level set psi equals c intersected with this small ball is just this curve, right? And then it's easy to see. And then from the fact, but at the same time, you have a sequence of times converging to y, right? At the same time, you have a sequence of times starting from x. So you have phi n1 is here. This makes sense for everybody? It's clear? And this tells you, okay, so just use the group property. So here, since psi is autonomous, you have this group property. So for any, let me just keep z for now. If you flow time s plus t, that's just the same as flowing time s and then flowing time t, right? So this is fundamental property of autonomous flows, right? So that means if I take, so this point, phi of x n1, and this point, phi of x n2, those are the same as, because of that, those are the same as phi of y, epsilon 1, and that's phi of y, epsilon 2. Isn't that right? Is everybody following? Is this too easy? Maybe it's too easy. But, okay. So that means that, so if this is the case, so if you just flow back by epsilon and epsilon, you get phi of x epsilon n1 minus epsilon 1 is phi of x n2 minus epsilon 2. Okay? And these clearly cannot be the same numbers, right? Because epsilon is a small number and n1 and n2 are integers, right? So that's it. Okay, so this is just the proof. So we could have told you from the beginning it follows by the Poincaré-Bendixson theorem. And I guess here this would be completely acceptable, but I think most of us don't remember the proof. And I'm not sure why it's true. So I just okay. All regular points have a periodic trajectory passing through them. Okay, so you can prove, so it can be shown. So next fact. I don't know how many facts I've stated so far. So next fact, maybe it's number 4. The period t of x is a C1 function. Okay, so I should have said that the set of regular points is open, right? So if you have a regular point, all the points around it are also going to be regular points. So if you have one periodic trajectory here, all of the points nearby will also have periodic trajectories, and the periods are going to be almost the same, but they can change infinitesimally. Okay? So let me give a definition. So if psi, so if t, so psi is called isochronal if t is identically constant on the domain. Okay, so the isochronal, this means the same time, right? So all points have the same time, same period. That's isochronal. Okay, this is a very, very special property. It's probably not very generic in fluids, particularly, but it does exist. So, for example, if you just take circular domain and you take the Hamiltonian to be x1 squared plus x2 squared, so if omega is just ball of radius 1 around 0. Then all of the periods are 2 pi, right? Or maybe, sorry. Then all of the periods are 2 pi. Okay, just solve the ODE is just phi 1 dot is minus phi 2. Phi 2 dot is phi 1. Okay, so it's all just going around 2 pi, period 2 pi. So this is like a solid body rotation. But basically any other steady state on psi will not be domain will not be isochronal. Okay, for Euler. Now, if you think about if you draw any streamlines you want, you can always make it isochronal. By the way, so if you draw any curves you want, you can always define psi so that it's constant on these curves and isochronal. But it's like a very strong condition.
You say that angle always reduces problem to isochronal.
No, if you wrote this in theta and r, you'd get that it's just a translation. Okay, that's what isochronal is. You just translate along the curve. Okay, right. So for any isochronal flow, you can reduce it to this ODE, change variables. Okay. Just a remark that you remember I said that cellular point, like the point in the cellular flow, is not really a not regular point, right? Because you can define the limit of the period, right? So for a center, you can always define the limit of, if it's smooth, you can always define the limit of the period. So the center is not really a issue. Issue is like a hyperbolic point. Okay. So now let me give a small lemma. If psi is not isochronal, okay, which is most of the time, then the gradient of the flow map bounded. Okay, so actually, let me make a more precise statement, more useful statement. So if t prime of x is not 0, then this is true. Okay? So if you have a point x, if x is a regular point, and the derivative at the point, derivative of the period at the point is not 0, then the gradient of the flow grows linearly. Okay? And that's sharp, right? So if you have a regular point, you can't really have anything else. So actually you can say that. Say that again? Then it wouldn't be called t prime of x, right?
T is going to plus infinity or to minus infinity?
Say that again?
T is going to plus infinity or minus
Plus to infinity, sorry.
both sides?
both sides. Okay, so this is not terribly difficult computation, actually. So I should remark that everything I'm talking about, there is this idea of like action angle variables, which personally I find a little bit annoying to deal with. So everything we're going to do is kind of just, we try to find the right values in the original coordinates, and that's it. Okay, so let's go. Maybe I should tell you why it's true first. Before that. So let's say here, a point that starts here and a point that starts here. Okay, and they're a small distance apart. Now suppose that the period here has the period here. So let's say, so this is the amount of time it takes to go around. Okay, then you just look at these points and draw a straight line connecting them. Okay. In fact, you can draw cheating, because we'll talk more about this way of looking at it tomorrow, but you should have a picture in your mind. So let's look at the evolution of this box. Okay, so this box is just going to go around and round, right? And the area of the box will remain constant, right? But if these points are going to go around the center circle in time t1. So let's just say t1 is less than t2. After t1 will only have gone around t1. So the inside will over t1 loops around 0. Okay, so let's just say 0 here. Whatever. Yeah. And the outer one will have gone around t divided by t2 times. And then you see that the length of this curve must have gone very, very long, right? Must have gone very, very long. The length of the curve goes to infinity linearly, which means that these two sides have to approach each other. So the sides approach. So the distance between the sides. So the minimal distance between the sides t, which is the same as gradient growth like t. Okay? Does that make sense? Okay. Okay, so let's just prove the lemma analytically, because sometimes it's useful to have a formula. It's a little cumbersome, so hopefully there's no mistakes. Okay, so we have that phi of x comma n t of x. So this is time, right? T of x is the period. So if I go n times t of x, where am I? I'm back at x, right? So that's x. Okay, so little n is very large. What will happen if I take the gradient of this equation? What will happen? Is the n going to stay inside or is it going to come out? Okay. All right, so let's just take the gradient. Okay, so then, so I have some difficulties with matrices, so I'm just going to write it in components. So for each I, this is I, and you get the gradient of phi x. So that's the first term. Plus so now I'm getting confused. ddt okay, so I just take di of both sides. Okay, this is potentially very embarrassing computation. Okay. So I forgot to say something, but okay, so let's just multiply by say that again?
The gradient. dt phi I.
So this is di. This is correct. And then so if I'm not mistaken, correct statement is that okay, so all I'm doing is multiplying the equation by di of psi. Okay, so I just take this equation, I multiply by di of psi. Okay, and that's just the statement. Now, everybody see that? Is that okay? Sorry. So you just multiply by the I of psi. And now observe that this thing is just grad perp of psi evaluated at x sorry, it doesn't make any sense. Evaluated at phi x and t of x. right? Is that okay for everybody? So this is just the ODE. Of course, phi xn t of x is just x. And so you get that the gradient of phi at this time in this direction is just gradient psi minus n times okay. So this identity should already tell you something, because all of these on the right side, with the exception of n, all of these are independent of time. Right? So these are all functions of x. Right? So you're fixing x. So this all depend on x. Right? So unless this thing is 0, right? Unless this thing is 0, you have growth like n, so linearly in time. Does that make sense? And okay, so why is this not 0? So this could be 0. But if you think about it, so what does this statement mean? So they have to have the same period, right? So already the t t has to be a function of psi. If you don't like the statement, which is okay, and if I take the perpendicular gradient of t, that I should get 0. So period should not change, right? Which normally is the same as what I crossed out. So the perpendicular is 0. So this better not be 0 if t is 0, right? So this is not 0. And this is not 0. So it grows like n. So the statement is that if you take the gradient of the flow map in the direction of psi, and then look at the perpendicular direction, this will be like t as t goes to infinity. Okay? So in the case of, for example, a shear flow, so this is one. So I should remark that so all other functions are bounded. So if you took perpendicular gradient is bounded. Gradient is bounded. So these are 4 components of the gradient of phi. Only one of them is unbounded, which we know from the basic examples. So if you look at examples of a shear flow, so if you just look at like sine of y, cosine of phi 2 dot. So if you look at this example, the flow map is exactly right. This is the flow map. right? If you have a shear flow, simple thing like this, where phi1, so psi is just a function of one variable, then phi1 dot is cosine phi2, phi2 dot is fixed, so phi2 is just y, that's this, phi1 is x plus t cosine y. So you see, when you take the gradient, you really only get one component that grows. It's dy phi1 that grows. Okay, does that make sense? Any question? So that's what this is. So if psi is a function of y, this becomes dy of phi dotted with phi1, with E1. Does that make sense? Okay. Okay. Let's mark that. Now, if you come back to the transport equation, so I'm going to 3 o'clock, right? Three. It's not. Don't worry. It's not that long. It's just. It'll be over soon. Okay. Okay, so now basically a corollary of this computation. So it's really it's not exactly a corollary of the lemma, but a corollary of that identity I wrote up there, right? Is that if you have, so if we solve the transport equation, where u is perpendicular gradient of psi. It's time independent, right? Then, wait. And if the gradient of f, if f is not like a steady state, then the and if psi is not isochronal, so everything I'm saying is basically and only if actually. And if psi is not isochronal, then the gradient of f grows linearly as t goes to infinity. And you can make more specific statements if you want, you know, like localized around a single point or anything like that. Okay, does that make sense? So I make a remark that I'm not really going to talk about at all, but so just to make a remark. So you can also deduce mixing statements. So this is, so I guess tomorrow, Michele speaking tomorrow, I think, We'll talk about this. So mixing statements. Using those identities. Okay, so that's all we want to know about the autonomous transport equation. Any questions? Any questions? Okay. Yes.
Isochronal was defined as the period being constant in all the domain.
Yes.
But in this statement, it can be constant locally in a portion of the domain. Then do you have still this statement if the initial datum is supported in that region?
Good point, right? So this should be true in a region where it's not isochronous. Yeah. Yeah. Thank you. Yes.
What are those singularities occur?
Say again?
Where do the singularities occur? Do we know singularity with what we did before? Or
Do we know like what the nature of this growth is? Yeah. Where?
in the domain?
Yeah, at any point where this is not 0 and where the derivative is not 0. So if this is true, if this is true and this is true, then, okay, I have to check just to make sure, but I'm pretty sure that this is true. In the autonomous case,
Even with the torus,
yeah, you can be on the torus, so it's confined to compact domain. So the statement should be, so it's in my notes, which I foolishly did not to follow. I believe the statement is that if you have at a single point, this is not 0, and the time derivative is not, the derivative of the period is not 0, then so it's a scalar function, but you really should write it like that. Then this should also be true. So you don't need really L infinity. Okay. One should just check, but I'm pretty sure that's true. Okay. Yeah, so basically, you kind of know what's going on. In fact, you can prove that, again, in regions where this is not convergence to the average along streamlines, which is mixing. And so you basically know what you need to know about this. Okay, I should say that as you approach regions where the derivative can become 0 or become very large, it's not really clear exactly what happens yet, even in the autonomous case.
Maybe you can C depends on X. Right?
Say that again?
Constant C.
Yeah, of course. Yeah. Yeah. Okay. Any other question? Okay, I haven't said anything yet about Euler. Okay. So, all right. So let's do that. Okay. So now I'm going to state and prove a theorem that was proven by Herbert Bach. So this is a version which is not very different from the more general version. So I just state it just to keep it simple. So we say assume we have an Euler solution, a C2 solution, omega. Okay, so omega could be stationary, could be not stationary, could be periodic. And let mu of t be the quantity which we've been talking about, which is the gradient of the flow of its velocity. Right? So omega is the vorticity, you get its velocity, and then you get the flow map. Okay? And this is L infinity in space. Okay, so you look at it at time t. As we saw in velocity fields, this is going to be infinity, right? But okay, let's not worry about that. Now, epsilon, okay, they are completely independent of each other. Okay, capital T will be very large potentially, and epsilon will be very small potentially. Then there exists omega 0 bar, which is C1. In fact, it's C infinity. And it's epsilon close to omega 0. So always omega 0 is associated to omega, right? And C1, it's epsilon away. But at time t, the solutions have apart basically exactly how much you would think. Okay, and the 1/2 can be like 1 minus, delta.
Omega bar is the solution of Euler equation with
Omega 0 bar, yeah. Okay? So in particular, so let me just say, in particular, if omega was a stationary solution that was not isochronal, so like a shear flow or something like that, then mu of capital T would go to infinity, right? That means that if you consider a point very close to omega 0, you can make its C1 norm grow as much as you want. You can go from epsilon to capital N for any epsilon capital N you want. Does that make sense? So this is like, so this implies based on what we said before, so corollary. So if omega star is in non-isochronal. It's like bad words now. So isochronal refers to psi. I'm going to make it refer to omega now, but it means psi. Okay. It's non-isochronal. So if omega star is non-isochronal, steady state then okay, smooth. Okay. Strongly unstable in C1. In the sense that you can have a perturbation of size epsilon that goes to size capital N away. Okay? And you can use this idea after I prove it. You can even use it to give infinite growth. Okay? Any question about the statement before we prove it?
What does it mean strong and stable? Non-linear and unstable?
Yeah, it means that you start with the data epsilon away. Epsilon away, and after a long time it goes capital N away. Okay?
Unstable in C1 norm or vorticity?
Yeah. Yeah, so, right. So we're going to talk about, yeah, so I'll get to that point. Yeah. Yeah.
So in some sense, it's telling that the C1 is not the right norm if you just want to look at stability issues.
Yeah, if you want to look at stability issues or long time issues, you really should not study it in C1. You should really restrict to the Udovich class or even less than that. You guys did the Udovich stuff last time, right? Last week. Okay. Okay. Any other question or comment? Yes.
But this is only from finite time.
So
So it could go back.
potentially, very unlikely, but potentially could go back. Yeah. Okay. Let me, so the proof, you would imagine by the statement that it should be very difficult to prove, but it's not very difficult to prove. So let me explain the proof. First, I give you a basic explanation, but also we do the infinite time stuff in the next few lectures. So the idea is to in weaker norms. That control the flow map, right? So you see when you make a perturbation that's size epsilon in C1, C1 of vorticity is almost C3, the C2 of the velocity, right? It's almost C2 of the velocity. What do you need to control the trajectories, to control phi and the gradient of phi? What do you need? What do you need from the velocity? Just Lipschitz, right? To control the gradient of phi in L infinity, you just need the Lipschitz norm of the velocity. So if you have So you have a big gap between what you're trying to measure and what you need to control the trajectories. Does that make sense? So for example, so you could take, will take omega 0 bar in C1 half to be very, very small, to be less than delta. Now, delta will be a function of t and epsilon. Okay, so it will get very much even smaller when t goes to infinity and smaller when epsilon goes to 0. Does that make sense? So if just from this, from wanting the C1 norm to be less than epsilon, the C1 half norm could be like super small. Yes?
C1 alpha is the Udovich.
Say that again?
C1 alpha. So Udovich or
Yeah, so if you have a data that's this close, as close as you want, essentially, in C1 half, you could think they're even the same function, right? And then the trajectories will be exactly the same. And if the trajectories are exactly the same, then you can put a perturbation. If the trajectories are exactly the same, say omega bar is exactly where phi is the 1 of omega. Does that make sense? So if they're essentially the same in C1 half, if the difference is effectively 0 in C1 half, then the trajectories will be exactly the same. Does that make sense? Then you can just apply what we did in the linear transport. Is that clear for everybody? Okay, so it'll be clear when I prove it, if it's not clear now. Okay, so let's state a few lemmas. So I'm going to give you the backbone, not going to give you all of the details, because you can easily reconstruct details. Okay, so lemma 1. A sequence of vorticities converging, say in C1 half, to another vorticity, omega 0. Then, for all t finite, omega of t minus omega n of t in C1 quarter goes to 0 usually on 0 to t. Okay? So how do you prove that? We all do the Euler.
the volume
Huh? Yeah. Did you all do the? Do you know the? So prove. What's that? You bound the relative energy. So what he just said is that if you take two solutions to Euler, you can prove, and if one of them has bounded vorticity, just whatever. But okay, here you have much stronger bounds, but you prove an energy estimate of that, right? So you just take, if you and Euler solutions, you just subtract the equations, right? And then you consider this guy, you do an energy estimate, and you get this bound. Should we do it? That's okay. All right. So you get a bound of this type. So this implies, so if you try to do this on the vorticity directly, you run into some small problems. One of them is smoother. Okay, so this is just it's more direct using it this way. Okay. Okay, then you deduce. So this oh, sorry. Maybe I should have written it more carefully. So you deduce a bound of this type. Of course, for any Euler solution up to time t, this will be a bounded number. So it means that from here, you know that the velocities converge. And once you know the velocities converge, if you have a bound on these, just an upper bound on this, have an upper bound, sorry, on the C1 half norm, then you can use this fact just by interpolation. Okay, does that make sense? So you just use interpolation. So if you don't see immediately how to do this, a good exercise. Okay, is there any question about that? Any question? Okay, second lemma. If omega minus, now we went down to C1/4, goes to 0 on formally T. Then if you look at the gradient of the flow maps, so you don't need to put the gradient. Phi minus phi n, W1 infinity. again, uniformly on 0t. Okay, so this is just continuous dependence on data. So order of vorticity gives you this convergence in C1 of velocity. So it's just ODE argument. Okay, make sense? This is what I was saying about the vortex. If you take the perturbation very, very small in, say, C1 half, then the flow maps are essentially the exact same. You can view them as the same.
The
Yes.
For any capital T fixed, if
Yes. Yes. Fixed capital T. Yes. Okay. Makes sense? Okay, now basically done. So now, omega solution. So let's remember what's the statement of the theorem. So you have omega, which is a solution, fixed solution, and you have omega bar. So let's set omega bar 0 to be plus omega 0 tilde. Okay? The inverse. Okay, that's always forget when you're doing this. Okay. Okay, so omega 0 bar composed with phi bar inverse. This is what I'm going to do now is very plus. Gradient omega bar. Oops. Sorry. I jumped. Oops, got confused. Okay, so this is just Euler, and this is just omega 0 composed with phi bar inverse plus omega 0 tilde composed with phi bar inverse. So gradient omega bar is just gradient phi bar inverse, gradient, well, let me actually keep this as just one thing. And I write this one out, so that's gradient phi bar inverse, gradient omega 0 tilde evaluated at phi bar inverse. Okay. Is that okay? All right. Now, what's my assumption on on the on gradient of phi. Gradient of phi. Okay. So now, given what I said, which is not here, it's there. Given what I said, I can remove this bar. Okay? Does that make sense? I can just remove the bar because the perturbation will be really as small as I want, independent of any of the parameters in the problem. Okay, so then all I'm going to say is that this is approximately omega 0, omega plus gradient phi 0 tilde. Now, okay, this is small annoying point. Here, I can't remove the bar. If I tried to remove the bar, I would have to use higher regularity of gradient omega 0 tilde, which would kill me. Because we're taking, if C1 is epsilon, C1 half is, very, 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 very small, then any regularity higher than C1 will be huge, right? Does that make sense? Just by interpolation. Regularity, so I cannot remove this bar, but I can remove this bar. Does that make sense? But I don't care actually about removing this bar, because this just says a point. You see what I'm saying? So now you choose omega 0 tilde so that at time t, whatever point is, wait a second, confused now. Just a second. Don't need to do that actually, so.
Well, we get the tilde is the small part, right? Should be so the trick you used should be used for the part, more than for the thing.
Removing the bar?
Yeah.
Yes. Yeah. The first part, that's fine. There's no problem with that, but you can't. I want to say how you choose this. Okay. I think now if you consider now you compute this guy. Okay. This is a little yeah. So right. Okay. So what you're going to do, so instead of, you're going to consider this whole thing and evaluate here at phi bar. Does that make sense? Is this clear for everybody? And now you can remove the bar. Okay, so now you can say this is gradient omega plus gradient phi opposed with phi. Yes?
Can you explain again, please? I'm sorry. I was a little bit confused. Why can you explain more once again?
Okay, start over. Okay, so we have an initial data. That's a perturbation of our original one. Okay? And it's a perturbation so that the flow maps are essentially the same. Okay? You can view the flow map of phi as basically the same as the flow map associated to phi. Yeah. Basically, as long as you do not use higher regularity of this. Okay? Does that make sense? Okay. This is Euler, this identity. Now I take the gradient. And now I say I have this part. Now omega 0, you assume is some nice smooth function. Right? It's a given thing. It has nothing to do with the perturbation. So when you say that this thing is approximately the same as omega 0 composed with phi, that's true. Right? Phi bar is almost the same as phi, and omega 0 is a fixed smooth function. You see what I'm saying? Is that clear? So this thing really is approximately that. Where approximately means when delta goes to 0, independent of epsilon and capital T, this really converges to that. Okay? In C1. So in L infinity here. Okay? So this to this is fine. What about this one? This one, okay, this is exact. I haven't done anything yet. Now, gradient phi bar inverse. Again, I can add and subtract gradient of phi inverse. Is that clear? This goes to 0 very, very fast. And I don't use anything about omega 0 tilde. Is that clear? So you're left with this. Okay, so now I just remove this bar. I put an approximation. Okay, so you forget about all this. And this is just that. Now, here, right, this is the perturbation. I'm going to have to choose it, right? What you would like to say, what I was about to say, which was wrong, but what you would like to say is that you choose the perturbation so that at time t, you make, so you know that the gradient of phi, inverse is like mu of t, right? The gradient of phi inverse psi. Okay? You know that the gradient of phi inverse is like mu of t. Okay? That means that there's a vector v for which this is mu of t. It's bigger than, well, there's a vector actually where it's like that. Okay? So there's a fixed vector so that at time t, this thing is mu of t. Does that make sense? That's what it means for a norm of a matrix, right? So now you want to choose thing so that at time t, you want to choose this so that at time t, it takes v here. You want to make this equal to v, right, times epsilon. Does that make sense? You could do that if this was phi. If it's phi bar, you don't really know what phi bar is, right? To change phi with phi bar here, you would incur some regularity of this, which you don't want to use. You know what I'm saying? Okay, so all you do is you make this large. And that's. Does that make sense?
So it's the last part again. The last line.
Yeah. Oh, sorry. You can now remove this bar and make it phi. And now this is something you know. This thing inside here, you know what phi is.
But you still have the bar.
No, but that's where it is. You don't care where it is. Yeah. Okay. Does that make sense? So we're going. Oh wow. Okay. I missed like the fact that we went way over time. Sorry.
Excellent.
Yeah.